we're actually going to talk about containerization. Now, before I do that, this webinar will last an hour, and the slides that you see before you here will actually be shared with you, ranging from the Kubernetes architecture to the actual workload types on Kubernetes. Now, there are other slides that I may show you, other websites that I may link to, but this is the primary slide deck that will actually be shared with you. Okay, so let's get started. So as you may or may not know, Kubernetes is what's called a container orchestrator. And so the main idea behind Kubernetes is basically to solve the problem of how do we run containers, particularly of which Docker is one of the most popular versions of containers. How do we solve this problem to run containers at scale across a lot of systems? But that does presuppose that we understand a few of the fundamentals around containers. So to do that, I'm actually going to borrow from an official class that Web-based Solutions teaches in conjunction with AWS. And it's the running containers on an Elastic Kubernetes service class, where they talk about the fundamentals of containers. And so just to show this and share this for just a second. So when we talk about containerization, particularly when it comes to the fundamentals of containers, this is our world as it existed prior. Meaning that our main challenge here was that we had a number of ways in which we could package applications and then in a sense ship them out to production. And whether it was you were using Spring Boot or Capistrano or Sinatra or all of these other packaging frameworks, it was a little bit chaotic. And then of course Docker came along in 2013, 2014 and started to propose the idea of what if we actually did this? The problem of standardizing shipping containers in the real world was solved in 1958, if not earlier, when two gentlemen basically patented the concept of let's provide a rectangular container, and whether there's bananas or microchips in the container, the shipping industry can have one standardized system or framework for dealing with these rectangular containers. We can stack them easier. We know how to power them. We know how to cool them. We know how to ship them. We know how to put them on other vehicles other than ships, like trucks, for example. So what if we could standardize this in software as well? And that's basically what Docker proposed back in 2013, 2014. Let's come up with a standard format. Now, to be clear, the concept of standard packaging existed with BSD jails. It existed with Solaris containers. So this wasn't necessarily a new idea, but Docker was the first to actually make it democratized, where it was actually relatively simple to put your process inside of a container and standardize it. Now, at this point in time, we were used to bare metal servers. We were used to running operating systems. And in about 1999 was when VMware released their first product. 2003, if my memory is correct, is actually about when they released ESX, which was the server data center version of their basically virtual machine software. And this is where we've been for the last, now 18 years, 19 years, 20, right? Where we've been running virtual machines, and inside of these virtual machines, there's a guest operating system that sits on top of a virtualization platform, which can sit on top of an operating system, or the virtualization platform can be embedded inside the operating system like it is with ESX or vSphere or any of its derivatives, right? And so we still have an operating system now that's acting as the interfacing layer between the server hardware and the virtual machines. Now you might call that a hypervisor, but it's still an operating system. What if we could remove the guest operating system out of the equation, and instead of doing OS level virtualization, what if we could do process virtualization? And this is, by the way, where containers really start to shine. Is that now instead of having to abstract an entire OS, we're just going to abstract all of the libraries associated with the process. Because just to be upfront about it, you can run an Ubuntu container, but you're not running an Ubuntu operating system. You're running the binaries for an Ubuntu operating system. Because when you run a container, the container actually shares the kernel with the host. So when you run an Ubuntu container on top of a, for example, RHEL Enterprise Linux host, You're actually running those Ubuntu binaries against the Linux kernel that's inside of Red Hat. So with that in mind, containerization takes away all of the headaches of managing a guest OS, which is what you can see right over in the pink, or the guest OS under the virtual machine section. And instead, you're now running many different processes that are actually isolated and jailed from each other. And this is the new world that we seem to be heading towards. Because what we're finding out now is about half of all companies have already an investment in containerization, and you're seeing less and less virtual machines and operating systems playing a role. As a matter of fact, you see the guest operating system, its importance just shrinking more and more and more, where we're actually going to leaner operating systems whose sole job it is actually to run containers, right? That's where we're headed. Now, this, of course, allows you to be portable because now your application is all packaged up. Obviously, it's scalable because you just scale horizontally. And then this allows you to run that container on any operating system that has the translation software. In other words, if you're running Docker and you have the Docker engine, or the runtime, if you will, containerd on your system, then guess what? You can now run that container anywhere. And Kubernetes handles that for you because it solves the problem of distribution. And then what happens is that this now enables microservices. If microservices make sense for your environment, right? There's interesting because microservices are touted as a way to get cloud native scale, but not all of us need microservices, although most of us could use a lot of the core concepts of microservices. And so containerization has also risen with this idea because microservices are independently scalable and they solve one business problem, like a particular business domain, such as inventory or email or marketing. And so containers are ideal for this because now we can separate our traditional monolithic architectures into microservices if our teams and our business needs that. Now, a container image is just a set of instructions defined inside of a Docker file. And what happens is that every instruction actually creates a layer for a container. And then when we deploy these container images out onto Kubernetes, for example, what happens is that it actually creates a thin read-write layer on top of it. We can also attach volumes to these containers if we want persistent storage. This is important to know as we move into the discussion for Kubernetes, because typically containers are stateless, but if you want to put a database in one, you can. You just now need to add a volume or some kind of persistence to the equation. Now, when we write these Docker files, by the way, we just add instructions and we expose ports and we copy files. And each of these layers stack up to build these images that we actually pull down either off of hub.docker.com or we pull off our own private Docker repositories, right? And so that's how the containers are built. Now, you might then say, well, then what's Kubernetes' role in this whole process? Like, what is Kubernetes actually going to do for us? Well, Kubernetes, running a container on a single host is actually easy, right? We've all got laptops, we've all got virtual machines, and we can literally just, Docker run whatever we want, and we can create whatever images we want locally. But what about this problem? What if we're here? Oops, sorry. What if we're here and we've got to run hundreds of hosts with thousands of containers? Like, for example, by default with, I think, Kubernetes 1.18, you're going to run about 100 containers, what they call pods in Kubernetes parlance, pods, right? You're going to run about 100 containers per host. So if you have 50 hosts, let's say you max out and you're running 5,000 containers, who's going to manually do this? Who's going to manually make sure that this happens across all 50 hosts? Well, that's the problem that Kubernetes solves. Kubernetes solves the problem of scheduling containers, placing containers, how to integrate container infrastructure with cloud, how to do all of the networking. Can you imagine the networking for this if you had to do it manually? It handles things like load balancing, how to attach volumes to those aforementioned containers that you might want to run databases in, and how do you handle security, monitoring, and logging. This is what Kubernetes was built for. It was built for this explicit purpose and reason, which is to solve these problems. Now, Kubernetes as an abstraction layer works well with containers to make things portable, to also do scalability, and to also enable continuous deployment, because you can now quickly deploy containers in seconds instead of waiting somewhere between 5 to 10 minutes for a virtual machine to boot. There's also a strong community. It's cloud deployable, and of course, it follows a declarative format that you can also check into a repository just like your Docker file from your container side of things. Now, a declarative format versus an imperative format. Remember, a declarative format means I want you to follow this instruction, this instruction, this instruction, and this instruction. That's imperative, right? That's procedural. Follow these steps in this procedure. A declarative format says, look, I want a rectangle with a width of 300 and a height of 100, and I want it to be the color black, so just draw it for me. And by the way, start it at this position at 100, 100 on the XY coordinate axis. And so declarative format says, here's my end state. I just want you to get there. And that's a lot of what Kubernetes does. You just give it an end state, and what will happen is that Kubernetes has a container orchestrator will orchestrate what you've declared you want your desired state to be. Now, Kubernetes objects, there's a couple actually that make up Kubernetes, but before we dive into that, let's slide back to our original slides, and let's talk a little bit about the architecture, because that will actually help make the objects make a lot more sense. Now, just a side note, this is primarily a lecture, but just know that if you type a question into chat or into questions, chat is probably preferred, but questions I'll answer in there as well. I will actually answer it as soon as I see it, especially if it's relevant for what I'm talking about, but we will also have Q&A at the end for the last 10 minutes or so, in case someone has something burning. All right, moving on. So Kubernetes derives from the same word that Kubernetes or governor, gubernatorial, right, derives from, helmsman or pilot, leader. It was actually originally founded by some people over at Google. It was actually part of like the Borg project, also known as 7 of 9, which, by the way, if you ever look at the Kubernetes logo, that's why there's 7 sides to the logo. Even though there's an 8-sided wheel inside of it, there's 7 sides to the logo, because that's a reference to 7 of 9, which is where the project was originally kind of sourced in, right? Now, Kubernetes is often associated with Docker, but Docker is just one of many container runtimes. Anything that will support the OCI standard for containers, Kubernetes can manage. So whether that's Containerd or Creo or any variation thereof, Kubernetes can manage the system. So, by the way, Kubernetes just needs an operating system to run. So if you have a virtual machine or a piece of physical hardware, or even a Raspberry Pi, and you want to run Kubernetes, you can. If you want to do it in the cloud, you can. Not only can you do it in the cloud on virtual machines, you can do it in the cloud on any of the managed service providers' version of Kubernetes. AWS has EKS, Microsoft Azure has AKS, and Google has GKE, the Google Kubernetes Engine. And, for the most part, they all have certain pros and cons, but they're just pretty spectacular because they're basically all just Kubernetes. They're all just upstream Kubernetes. There's nothing super special about them other than what they abstract away and take off your plate when you're running Kubernetes. Now, since container orchestration is the primary responsibility of Kubernetes, one of the things that we want to talk about is what is the architecture here? So if we look at this little diagram here, a Kubernetes cluster has what we call a control plane, and it also has what we call a data plane. Now, the control plane is a Kubernetes control system, is what it is. And it's comprised of things like the API server, which, just so we're clear, everything in Kubernetes is an API. Every object is just an API. And then you have a stateful database called etcd that maintains the configuration of everything going on inside of Kubernetes and on the actual container pods themselves. And then you also have things like a cloud controller. You have a controller manager. You have a scheduler, which is used to schedule pods. And then on the worker nodes, which you see on the lower right-hand side here, you always have a kubelet, which is mainly responsible for interfacing with the control plane. And then you have what's called kube-proxy, which helps with all that crazy networking configuration that you have to do with Kubernetes. And by the way, Kubernetes is not a panacea, and running plain vanilla Kubernetes just out of the box, like orchestrating yourself, is a great learning exercise. It's also a great exercise in pulling your hair out. Because Kubernetes is an awesome piece of software, but it does have a little bit of a learning curve with it because it's brand new. We haven't been doing Kubernetes for about 5 years now, maybe 6 years. And so we're not in our 15th year of running Kubernetes like we are with virtual machines. We're in our 6th year. And the software is getting better and better and better. But just know you want to know the components in order to save yourself some time when troubleshooting and setting up your system. So note here, by the way, in this diagram, you can see something called the CCM at the top, which actually looks like it's talking to a cloud provider API. Kubernetes is typically cloud aware. So it will actually integrate if you decide to run it on your own virtual machines in AWS, for example. It will actually create load balancers for you. And if you add the Cloud Controller Manager for AWS, which was just released about 2 months ago, you can literally use Kubernetes to spin up AWS objects, just making them part of your Kubernetes cluster. So this could be RDS databases, this could be DynamoDB, this could be S3 buckets. It's just up to you how you want to orchestrate it. So remember, there's 2 components on the worker nodes that actually host the applications, the kubelet and the kube proxy, which are on the lower right-hand side. And there's anywhere from 5 to 6 components running on the control plane on the left-hand side, which includes the API server, the controller manager, the scheduler, and etcd, the database, and optionally a cloud controller manager if you're running on cloud as well. So that's the basic kind of internals architecture for Kubernetes. And by the way, that comes straight from kubernetes.io. If you're looking for your own picture in this particular case. And so there's a couple of pieces that I want to remind you of that make up the Kubernetes cluster. So the cluster itself is a mix of typically what you have, what are called 3 masters. We also call them 3 control plane boxes. And then we also have worker nodes, and you can have up to 5,000 worker nodes in a single Kubernetes cluster. 5,000. That's a lot. By the way, that's a lot of machines inside of a single cluster. Now, the master nodes, also called the leaders, they're responsible for managing everything that goes on inside the cluster. And the node or worker node or application node is, again, where everything runs. It's where the applications all run. Now, Kubernetes has this deployment unit called a pod. And a pod is typically only one application container, although sometimes there can be more, but typically there's only one application container in a pod, with either one or more security, networking, or operational containers inside the same pod, but there's usually only one application container. So when you run Nginx, there's one Nginx container in one pod. So if you want 3 copies of Nginx, you have to run 3 pods, right? Because there's only one application container in there. And the reason we do that, by the way, is for scalability. Since Kubernetes manages pods instead of managing containers, when it moves the pod around, it moves the container around. But you don't want to scale your Nginx front end at the same time that you scale your MySQL server. So you wouldn't stick your entire application in one pod, because what if you only need to scale the front end? You don't want to start 5 MySQL servers when all you need is 5 Nginx servers. So remember, the pod is the basic unit of deployment, and it typically contains only one application container. And I mean whether that's a database application, a web application, right? Doesn't matter what type of application, but usually there's only one inside of a pod. Now, you can associate a volume with the pod, if that makes sense, which is basically giving it storage. Where does the storage come from? Well, what do you give your host? Are we on AWS? Are we on Azure? Are we on GCE? You can actually use pretty much any NetApp, cloud-based, or any kind of network-based system that you have, Kubernetes will actually have a volume driver for it, and you can present that actually to the pods and therefore the containers inside your system. Let's see if we can get a little better visual on that, just to make a little bit more sense. So here we are, and we're running our Kubernetes cluster, and we've got a worker node. And that worker node has pods, and those pods have containers in them. And what happens is that every time Kubernetes moves that pod around to say another worker node, because say one failed, for example, it's going to take that entire gray box and it's going to move it. Now, by default, when you start a pod inside of Kubernetes, which has a container in it, nobody outside of the cluster, outside of that Kubernetes cluster, can actually see that application. So you can't get to your web server until, in a sense, you expose it out to the world. How do you expose it? Well, use what's called a service. A service, of which there are 4 types of services as of May 2021. A service is a way for you to basically either expose an application either internally or primarily externally. So for example, excuse me, in this particular case, we want that web app on the left-hand side to be able to get to the back end. And so the back end's actually listening on port 80, which is great, right? But the back end's actually listening on 13.721, and that service is actually taking traffic on port 80. Excuse me. Sorry about that. A little choking there. I apologize. So what ends up happening is that with port 80 taking traffic on the system, 13.721 is actually on the back end listening. And so web app is actually talking to this virtual object called a service, and that service is redirecting traffic to the back end. By the way, since everything is actually defined as a YAML file in Kubernetes typically, although you can create these things manually if you want to, you're going to see throughout this what they call pod specifications. And this is a document that defines an object, like the kind of which is called a pod. You can see it actually on the top left-hand side. And this pod contains one or more containers. Now, in this case, you can actually see that it is pulling down the 1804 Ubuntu container. And so you have Ubuntu 1804 right there, and it's actually echoing hello world. And it's actually mounting a volume for Redis, which I'm assuming this Ubuntu image is either going to be running Redis or it's running Redis already. And this, by the way, these kind of YAML files, this is how we define objects inside of Kubernetes, because then we can check these files into repository, and now we've got some kind of infrastructure as code, but also some level of repeatability. Now, there's other objects inside of Kubernetes that we can also use, such as namespaces, which is basically a virtual slice of a cluster. And we can also annotate and label our objects, like our pods in Kubernetes, so that we can get some measure of control over whether we shut them down, whether we move them, whether we start them, or even where we schedule our containers. Now, we talked about the master node. We talked about the controller manager. We just talked about pods. By the way, each pod gets a unique ID. So whether I start 10 Nginx pods or 100 Nginx pods, every one of them will typically start with Nginx or whatever other name I give it, and a random hash, so that we can make sure that I don't have to worry about duplication when I start 5 copies of the same application. Because remember, Kubernetes is really good about enabling horizontal scale. And so in order to do that, you're going to have multiple copies of the same application. So by the way, once you're inside of a pod, once you have access to a pod itself, you actually have the ability to communicate to any container that's inside that pod. So by the way, this is why you have one application container inside of a pod, and you might also have security and operational containers inside of a pod. So if we go back to our visual that we were looking at before, you could actually have, as you can see here underneath that volume pod right there, there's actually multiple containers in that pod. But Michael, you might be saying to yourself, you told us that typically you only run one application container in a pod, and that's true. Maybe Nginx is actually inside that pod that has that volume with those 3 containers inside of it, but the other 2 containers, maybe one is a logging container, and maybe one is a security container. So just remember that typically inside a pod, you'll run one application container, but you can have many containers inside of a pod. But typically, they're actually kind of operational, security, networking, authentication containers. And by the way, this is how service mesh works as well. If you decide to run Istio or some other kind of service mesh, it sticks a sidecar container inside of your pod to intercept all traffic for you. Now, other than deploying applications, you can also do things like deploy what they call config maps, which you can think of them as better ways of doing environment variables. So you can actually define environment variables inside your pod. They usually look like files or mountable like directories, if you will. And they can actually be read by the application in the same location, no matter where it's running. And you can actually give it different information. So if the pod starts and it has a label of development, it might get a development config map. If the pod starts and it has a production label, it might start with the production config map. And this could actually tell it different things, like I want you to take up this much memory, or I want you to scale to this many copies, right? And if you have sensitive information, you can stick it in what they call secrets, meaning that you can do the same thing where you can actually inject into a container secrets that are contextual based on what environment the pod is running in. If the pod's running in production, it might get the username and password to the production database. If it's in development, it would get the non-production database. So secrets and config maps, by the way, are basically just key value hashes that look like files inside of your pod/container that you can just have your application read at boot time. And that way you can just get the information it needs. And now the configuration is now environment dependent instead of application dependent. I mentioned before that you can build these things using files. And so here's an example of a config map and the secrets that you can use, right? Now, I also mentioned that you can actually slice up clusters into what they call these virtual partitions called namespaces. And oddly enough, namespaces is one of the enabling technologies that even makes containerization work to begin with. But you can take a cluster and say, look, I want to divide it up into 2 slices. I want a monitoring slice and I want a application slice. Or I want a namespace for monitoring, a namespace for logging, a namespace for product A, a namespace for product B. You can actually divvy up your cluster into several different namespaces, and these namespaces act as security partitions. Now you have to enable that, but you can actually make them much stronger even than they are now. Now, when you deploy an application, you usually deploy multiple copies. And so when we deploy pods that are stateless and we want multiple copies of them, we usually deploy what's called a deployment. Isn't that weird? We deploy a deployment, right? But you can deploy other things like stateful sets or daemon sets or jobs or cron jobs. But deployments are one of the 5 workload types that you can deploy inside of Kubernetes. Now, when you make a deployment and you say, look, I want 3 copies of my app, the deployment object actually creates a replica set object. And that replica set object's job is to make sure that it keeps running the number of replicas you told it to. So like in this case, there's 3 backend replicas and there's 3 web app replicas. And so there's actually a replica set for each of these different deployments that basically says, oh, you're only running 2 backend services? Let me start a 3rd. So a replica set is an API object that monitors your deployed applications to make sure that the requisite number that you told it to run is always running. And that's all just a deployment. By the way, notice that the kind in the upper left-hand side says deployment, and then there's actually some labels here, but notice the replicas says 3, right? And so what happens with this is that this defines both the application that it's going to run, what port it's going to listen to, and the number of copies that it's going to run concurrently. Now, when we go to schedule these pods with Kubernetes, there's a couple of challenges. The first of all is that we need to find out, do we have systems that can actually satisfy our storage constraints? 2, do we have systems that can satisfy our desired set of resources? So just so you know, in Kubernetes, when you deploy a pod, a container, right, a pod, you can actually say, look, I want to start out with 600 megs of memory, and I want to be able to scale up to 800 megs if I need it, right? Because these are just processes, right? These aren't virtual machines. So we can give it more processor, we can give it more memory on the fly. You know what it costs us? Nothing. This is process virtualization. You can't do this with an operating system, but you can do it with a process, and that's what containerization is it's process virtualization. So you can add memory and CPU on the fly. It doesn't actually look like it's getting more like CPUs. It's just giving more access to the CPUs that the host has, right? By the way, one thing to note, you might be asking yourself, Michael, why does it say 600M for CPU? What does that stand for? Because you probably figured out that memory is megabytes or MB in this case, right? And you might say, Michael, what is 600M? So just so you know, in Kubernetes spec, every CPU is 1,000 milli CPU. That's one CPU. So with this request here where it says 600 milli CPU for container B on the right-hand side, that 600 milli CPU means it wants 60% of a processor. That's what it's asking for. So just know that 1,000 is one CPU, 1,000 milli CPU is equal to one CPU in Kubernetes parlance. So if it says 600 milli CPU, they're asking for 60% of a processor. Okay? Good. Now, by the way, notice here, we've actually not only launched this particular pod, this week, like resource quota, for example, but we've actually done it for a namespace. We've actually resource quoted a namespace and says, look, if you're looking for more than this in a namespace, this is your default, you're not going to run, or this is the max that you can get if you decide to run in a namespace. Now notice that this namespace is called staging. So you can actually set up a resource quota for every single namespace. So if you have Project A, and Project A cannot use more than 4 processors and 8 gigs of RAM, you can just resource quota the namespace. This is another reason why it's a good idea to put namespaces in your cluster on a per product or per application basis, so that you can either scope teams to use the resources they're allowed to, or scope an application to use more resources, to use the resources that you want to allow it to. Because can you imagine if there were no resource quotas and all of a sudden one application went rogue and crushed all the other applications because it took all the resources? You don't want that. So make sure that you're using resource quotas in namespaces and that you are namespacing your applications when you use Kubernetes. Now, we're back to scheduling, but we're trying to figure out, like, is there a host that has my right storage? Is there a host that has my resources? And is there a host that potentially it matches a name if I ask for a name of a particular host? Why would you want to name a host? Well, you might say, look, I need Windows. I have a Windows container. I need a Windows operating system. I run a Linux container. You need a Linux operating system, right? I'm running a machine learning container. I want a system with GPUs on it, right? And so those are all constraints. And so all those constraints work together to come up with a candidate list. It gives you a candidate of worker nodes that could run. And then the last thing that happens is that they do this thing called prioritization, where they basically help you figure out, okay, I've got 10 candidates. Who is my most favorable candidate, right? And by the way, you know what prioritization does, because it does what we would do. If you had the choice between a system that had 20% free resources and 80% free resources for your application, you would choose the one that has 80% free resources. Why? because you pretty much can guarantee that your system's going to run better on that 80% free than it is the 20%. And so prioritization just takes the list of available worker candidates and scores them. And then things get scheduled, right? That's what happens after that, is that things get scheduled. Now, we've talked about the control plane already. We've talked about the data plane, and we've talked about how controllers are trying to maintain certain states in Kubernetes. But just a reminder that these components actually make up the internals of the control plane. So that's the controller manager, the cloud controller, the scheduler, the API server, and the SED server. And then together we have the worker node plane, which is where all the pod applications actually run. And on this section, we have the kube proxy, the kubelet, and then any container runtimes we're running. So if we're running Docker, we have containerd on there. Or actually, we have runc in the shim, right? So if we're running Moby or Creo or something else, we'll have that on there as well on the worker nodes. Now together, the control plane and the data plane make up the cluster. And again, remember, you can have up to 5,000 worker nodes in a Kubernetes cluster, and typically you run three control plane servers, typically. Now, if we go back to pods, which is that basic unit of deployment, remember that we can actually label pods and we can annotate pods when we deploy applications so that we can control how we manage pods. One thing to note is that labels have like some strict prefixes, like they have to be 63 characters long. They can't contain any special characters other than dots, dashes, and underscores. But you can also annotate your objects inside Kubernetes, and there's no limit on what you can put inside annotations because that's just arbitrary metadata. And then we mentioned before about secrets and config maps, and that you can attach storage to your systems. So you can always make basically an ephemeral pod. You can make it stateful if you need to. We talked about resource quotas already, so I already visualized that for you. Oh, and then how do you interact with Kubernetes? Well, typically what most people do is they use a command line thing, command line tool, if you will, called Kubectl. Actually, let me blow this up just to make sure that you can see that properly. So they use a command line tool called Kubectl, and what you can do is you can actually get your pods off of Kubectl if you actually want to see everything. Now, of course, my demo, of course, is going to break right as I run it because in this particular case, you know, the demo gods are not necessarily kind. So I'm just going to go ahead and restart my virtual machine that has my Kubernetes cluster inside of it and see if I can get it functioning. But Kubectl is actually the command line client that allows you to interact with Kubernetes. Some people call it Kubectl, by the way. There's kind of jokes about it. The other way to interact with Kubernetes is that you can talk to the API directly if you can authenticate. So if you want to use another tool, or you can write in Python or Go or any other language that supports API interfacing, you can actually manage your Kubernetes clusters that way. The other really popular way to run Kubernetes is actually using the web dashboard. Now let's see, my cluster is still booting. So I'll have to come back and show you the dashboard, but I actually have a static version already up and running. And notice that I can't refresh this because my server is actually down, right? But on the left-hand side, it lists all of the workloads and the services and the config maps and the storage that I was referring to earlier. And then here we also have namespaces. So you've got your cluster roles, your cluster role bindings, your namespaces. You've got all of your what they call role-based access control listed here as well. Now just checking in just to see if it's booting back up. So those are the two main ways that people interact with Kubernetes, is using the Kubectl command line, or they use the dashboard application, but with the web UI, which I will show you that before we get there. Now, when working with Kubernetes, you got to know that basically Kubernetes will run on any piece of software. So Windows 2019, Windows 2016, any Linux server, I think it's like Linux kernel 3.10 and above, which I think we're on kernel 5 now. You just saw me. I'm actually on Windows, and I'm running a product called Minikube, Minikube. And Minikube is a great little product because it allows you basically to run Kubernetes as a virtual machine, a Linux virtual machine on your system. Now, note, by the way, that it should now be up and running. And so now when I do a kubectl get pods, it now shows me everything that's running on the system. And if I come back here to show you the dashboard, and I run Minikube dashboard, what happens is it's going to open an interactive dashboard that will allow me to click through things and show you things like config maps or storage classes or anything else that makes sense inside Kubernetes. Now notice that there's a deployment here, right? And this deployment, and I'm actually going to do all namespaces, this deployment will actually show you every single instance of everything that's installed inside of Kubernetes. In this case, you can actually see the metric server and some of the core components. And if we click into this Nginx controller, you can see details about where this came from, how long ago it was started, and what it's doing here, any replica sets or any other events that have happened with it. So the dashboard is actually really good for troubleshooting and for finding and hunting information. So is the command line, actually, as well. If we come out here and look at the various pods that are running, we can see that the dashboard pod is running right here. Here's the metrics pod. Here's the Nginx admission patches, right? Here, or controller, actually. And then here is the metric server, Elasticsearch, and Kibana are running in the system as well. So it's for logging and monitoring. So this is great. Yeah, so Matthew, to answer your question, so you find people installing the dashboard as a separate app because you can't actually run it inside of all the providers. I will say that when you're running in GKE and in in Microsoft and Amazon, you typically use the GCP console to manage the system that's around Kubernetes. And if you want to get inside Kubernetes, people will typically actually use the dashboard. The one difference, Matthew, to your point, is that GCP offers a dashboard that actually looks inside of Kubernetes really well. So many times in GCP land, you don't find yourself actually needing to run the dashboard because out of the three, since Google actually created Kubernetes, you could argue that they probably run it the best, right? Which means that their tools are probably a little bit more tightly integrated in with Kubernetes. It doesn't mean, by the way, that Amazon and Azure don't do it very well. But in GCP land, their console is actually very comprehensive. So that's actually a good point and a good question. So once you have, by the way, let's say Kubernetes installed in whatever form or fashion you want to, you can then use the kubectl dashboard or just API into the system. And then kubectl, by the way, will give you basic information, or sorry, let me rephrase that. kubectl will give you every piece of information that you want about the Kubernetes cluster. It'll give you everything about you can run stuff, you can delete stuff, you can do everything with kubectl, almost everything that you can do with the API. Just know that there are some things in the API that don't necessarily show up in the kubectl command line, but most of those are very fringe cases, so you're not going to run into that. You can actually just curl the proxy directly, assuming that you have authentication to talk to the API for Kubernetes, so just know that you can get in there and touch things if you need to. And then we just showed you the dashboard, so you saw all those pieces inside of Kubernetes as well. Now, deployments are the base workload in Kubernetes. So this is the main thing that we use to actually run containers. There are other workload types. So by the way, here's a couple of commands, and this will be shared out with you, so you get access to all these commands if you want to run them and check them out. For example, in this particular case, this create deployment, I'm literally just running the latest Nginx container. You can also update deployments, roll new versions, scale them, set up a new image. You can do all kinds of stuff, right? Now, the other thing to think about is that other than deployments, there's also other jobs in here, such as stateful sets, of which there's nothing to display here right now because I haven't deployed a stateful set. And stateful sets are interesting because this is where you would run your databases, your MySQLs, your MongoDBs, your whatnot. Because what will happen with stateful sets is that you can actually add persistent storage to any of the workload types that are over here on the left-hand side. But the thing that makes stateful sets different is that the naming convention doesn't change when the pod restarts. Like what? What are you talking about, Michael? Just so you know, when we go back and look at all these pods that are running, notice that they have a random set of letters at the end. When these guys restart, by the way, they typically get a new name. Now, that's typically not a problem for Kubernetes because Kubernetes knows how to find its own stuff. But if you're a front-end application looking for a database and you're using DNS to resolve the location of your database, you want the name to stay consistent and you don't want it to randomize. With stateful sets, when you actually create an instance here, it actually retains the name that you give it, even if it restarts. And so that way you can find it in DNS consistently without having to do like a label selector or some other kind of like interesting service discovery. The DNS resolution is actually, in a sense, its own service discovery. Now, other than stateful sets, there's also jobs and cron jobs and daemon sets. Cron jobs are just like the cron jobs we've been running for 20 years, right? 30 years, 40 years if you've been in the Unix world, right? Jobs are like batch jobs. So if you want to run something in parallel, like calculating pi out to a certain number of digits, this one you want to run a job. And then daemon sets are used when you need to make sure that every single worker node in a cluster has a piece of software running on it. For example, security software or logging centralization software or some kind of operational like monitoring agent. That's when you would run a daemon set in order to make sure that's running on every single node, right? Now, a couple of final thoughts before I stop in 3 minutes and just open the floor to questions. So in this particular case, right, pods running in K8s, by the way, are on their own kind of like isolated network. Pods, by the way, are visible from other pods in the cluster. And if you're running on a cloud provider, by the way, just note that you might actually find yourself, right, eating IP addresses off of, like, for example, your VPC and AWS. So remember that once you like use the actual managed services inside of, like, say, GKE and whatnot, sometimes they can operate a little differently. So make sure you read your provider's documentation, right? So pods, by the way, are not initially visible outside the cluster. And this is where using a service like makes a lot of sense. And remember, there's 4 types of services. One of them is meant for internal consumption only, and that's the cluster IP. The other 3 are actually used for external exposition, of which load balancer is probably the best, like the most favored type. You'll actually see that listed here. And just to be clear, load balancer does actually use other types to get the job done. But load balancer is where you're basically either internally or externally defining an object that is your entry point, usually like an F5 or an Nginx controller or an HA proxy or something like that. Or you can actually use cloud load balancers as well. And what this does is that when you define a service, you're saying, look, if you go to this IP address or this DNS name on this particular port, you will get access to the applications on the back end. The only one that doesn't really work like that is external name, right? External name is basically when you hit this service, you're actually going to get redirected to another IP address. Or sorry, CNAME. It's a DNS name, not an IP address. And so like that's used, by the way, when you want to like have an available like resource inside the cluster that you can hit, and it will actually redirect to a service that's outside the cluster. That's what external name is for. Now there's a question there where it says, why might one want to use a stateful set to access a resource reliably instead of a services? Don't services take care of the name staying consistent? Actually, Nathan, I think you could go either way, actually, right? So stateful sets, services maintain naming consistency for services, but they don't maintain naming consistency for the backend services. But you're right. Does that matter if the service, if the entry point will always point to the same service on the back end? I'd say you could actually go either way with that. But then what if there's other systems that actually aren't going to run through the service that need to manage those pods, right? And again, you could probably do that through a service. You could go either way. But I can't off the top of my head think of a use case where a service wouldn't necessarily be useful instead of actually running a stateful set. So I don't really have a good answer for that because I tend to stick with services, but I'm sure there's use cases where stateful sets offer some kind of better consistency or naming convention where you actually need to manage it. I tend to just use cluster IPs and load balancers for that, and that tends to solve most of my problems without having to mess with stateful set workloads. But maybe there's a use case that I'm not aware of. So remember, if you want to expose a service outside the cluster, you need to use a load balancer or a node port. Node port's not really preferred. And then you can use external name to expose the service internally to get to something external. And then remember, cluster IP, despite the name, which is a little bit more weird, right? But a cluster IP, despite the name, is actually an internal only linkage. So if you actually expose a service with a cluster IP type, that's actually for internal use to the cluster only. Okay? So we talked about namespaces, labels, annotations, and other useful commands, but all of this is actually contained in here. So if you actually want to run through and understand more about the networking, the services, and the deployments, it's all actually captured in this document, which we'll be sending out to everybody. Now it's 8 minutes till, and I hope that that gave you a decent understanding of the various relationships between Kubernetes objects, how the scheduling and placement and problems that Kubernetes solves, and also how all of this works together to basically create, right, a containerization system that actually can be deployed into production. Now, I notice there's a few questions coming in, so I'm going to stop talking, and I'm just going to end on this internal diagram right here. Let me get to it. Right, that basically just shows a quick kind of the internal and the worker nodes and whatnot. So let's see. Could you explain in more detail the relationship between clusters, namespaces, nodes, and pods? Absolutely, Anthony. So here's how I want you to think of it. At the very core is the container. Around the container, Kubernetes has a pod, and that's how basically Kubernetes manages the container, is that the container is indelibly associated with the pod. So every time you're running a pod, you're running a container, right? Now, by the way, you can have multiple containers in a pod, right? But typically you only have one application container, right? So what happens is that the pod actually runs on a worker node. So you can actually see on the left-hand side, it says worker nodes. That's where all of the pods run. So when Kubernetes goes to schedule a pod, which actually has your application container in it, it's going to run it on whatever free whatever free worker node is available to handle that pod. If you've got 100 worker nodes, it's going to find the best node for your particular pod. And if you want 5 of them, it's going to find the 5 best nodes for your pods. And it's going to run those pods distributed across all the hosts in the environment. Now, every single worker node, when you enable namespaces, it is a virtual, in a sense, logical slice of the worker node setup, the cluster, if you will. So if you've got a monitoring namespace and you've got a logging namespace, that is a virtual slice of the cluster that lives on all nodes in the cluster. So think of it as a security partition that your pods are going to be running inside of. And the cluster is all of these boxes. So the container sits inside of a pod. Pods are assigned and run on nodes, and they're assigned to run on nodes in a particular namespace. And namespaces are just logical slices of the entire cluster. And every single node that's inside the cluster is participant in the namespace. So you don't have to worry about, well, can I run on this node because it might not be part of the monitoring namespace? They're all part of the monitoring namespace. The minute you create a namespace inside of a cluster, you are virtually partitioning that cluster in those namespaces. So let's see, another question that came in is, what's the relationship between Kubernetes and Helm? Well, it's interesting because Helm is actually the package. It's considered a package manager for Kubernetes. And if you actually go and look at the CNCF landscape, CNCF, by the way, is the cloud native. Oh man, my brain just stopped working. The cloud native computing foundation, right? And if you go look at the kind of map that they have, and if you only keep graduated projects, what you'll see is that Helm is one of the projects that's graduated out there inside, right? You'll see Helm right here at the top. So if we take away all projects except for the mature ones, you'll see that Helm is actually this basically software deployment system for Kubernetes. Now, my only beef with Helm is finding good quality charts can sometimes be a real pain in the rear end. And I don't know that the community is rallying really strongly around Helm. So it's still a great tool, and I love writing charts for Helm to actually deploy software into Kubernetes. But I don't actually have it set up right now I do have Helm installed. Yeah, but I don't have anything set up for it right now. I don't have any repositories or anything. But what Helm will do is that Helm, kind of like Yum or apt or brew or chocolatey or any of the installers that just do it in a single command line, you can actually single command line install Helm against your Kubernetes clusters, and you can install a best practice, for example, MongoDB system into your Kubernetes cluster with a single command. You can also install it and then modify it. Like, you can pull down the charts that it uses, modify it for your environment, and then install it into Kubernetes. So think of Helm as like a software installer for Kubernetes for particular applications. What kind of applications? Well, Kubernetes works off this concept of repositories. Let's see. So Helm, by the way, is package manager, and so you actually get these charts, and these are, by the way, things like, let's say we're going to do Mongo, right? You can get like Mongo Express, right? MongoDB is up here. This is from Bitnami. And what happens is that inside here, there are what they call repositories that you can add to your Helm repo. And so, like in this particular case, if I literally just copied that command and actually just added that into my system, it actually adds the chart. And then what I can do here is I can actually just run this command, and it will actually install MongoDB into my system, right? Now, that's assuming that my Minikube system didn't crash together for some reason. Because I don't know why all of a sudden it's been crashing, and it just started that about 20 minutes before we started this whole process, which is, of course, why it's timing out right now. So I hope that explains that. So Helm is the basically package manager for installing applications inside of Kubernetes. Good. Other questions? By the way, Nathan, I saw your comment about chat. I didn't know that, so thank you for sharing that with me. Okay. Well, I'm Michael Forrester. This is with WebH Solutions. This has been great to talk about with you today. Just briefly kind of skimming through a couple of the architecture and components and the fundamentals of Kubernetes. I hope this was useful to you. This is actually being recorded, so we will share the recording with you. We will also share the 2 chapters here that you saw, which are actually directly from our fundamentals class, which also includes labs and other pieces. So if you have any questions or comments, please feel free to respond to the webinar organizer. Otherwise, it's been a pleasure hanging out with you. I'm going to give it about 60 more seconds in case anybody has a question. But this is the official close of the webinar. I hope you have a fabulous weekend. Please take Monday off and relax and chill. And I'm so sorry if I made a horrible noise on the line. And I appreciate you bearing with me on this fine Friday. So we'll catch you at the next webinar.